Hi, so welcome again. So we try to understand boundary layer displacement thickness and boundary layer thickness, right? In terms of as a concept, what exactly do we mean by that? And also momentum thickness, right? We try to understand conceptually what exactly that means, trying to get a physical feel for it. And we also did a control volume analysis to get a quantitative measure in terms of the usual variables or usual parameters that will be available to us. For example, the velocity profile, the size of the plate, right, on which the flow will be moving, right. So so we went to, so let us go and revisit the problem that we what we had started out with, right, regarding the sharp plate. What was the problem that we yeah, so let us go back there. This is all what we were doing, right. So this was so we've got so this is what we started out doing, right. So we said a sharp plate with length 1 meters, b 3 meters is immersed parallel to a stream of velocity 2 meters per second, right. Find the drag on one side of the plate and the trailing edge. Find the boundary layer thickness, which is this, boundary layer displacement thickness, which is this, and the boundary layer momentum thickness. Okay. So let us see how we will sort of go about this. Okay. So let me solve this for you, if you have not already done so, and if you have, do cross check. Okay. And if I am making any mistakes, do point it out. Okay. Because there are sometimes typos or things, or maybe some things that I said which is not right. So make sure you get back to me and say that that was wrong, or maybe you could improve that. Okay. So your feedback is very important. Okay. So let us find out the Reynolds number here, right. So what is the Reynolds number in this case? So let us find that out. This Reynolds number is basically, right, and in this case what I get is about 0.14 million, right. That is what I get here, and which means, given what the break that we were talking about. So laminar boundary layer is essentially when the Reynolds number is below 3 million, right. So therefore we can say that in this particular case, the boundary layer so I think it's very important to remember that of course you will be using formulae, right. You will be using formulae for both laminar boundary layers and turbulent boundary layers, right. But you have to remember to check the Reynolds number, okay, so that you know that what in which zone of flow does the boundary layer belong to, right. Is it laminar or turbulent, so that you use the correct formula. So that's important. Okay. So in this particular case, therefore, then CD is something that we had. These are things we learned the formula about, at least. Okay. So RE, right. So I'm going to skip the step, and what I get here is this. Okay. This is the value that I get. So therefore drag, right, is equal to CD, right, into the dynamic pressure, half rho, right, into the area, right. So CD is known, density is known, the velocity is known, right. Free stream velocity is 2 meters per second, and the size of the plate, so B and L are also known. So, what I get here is newtons, right. Okay. Then we also needed to know the boundary layer thickness, at the edge of the basically at the trailing edge. So, now we know these formula, right. We know this formula. So, that is basically right. So, in this case basically our x is the total length we need to traverse from the the leading edge to the trailing edge, which is basically the length of the plate. So, therefore, here this comes out to be this basically. So, or I can basically write delta by L is equal to that by REL, which we have already calculated, and this comes out to be 0.0135, the thickness, right. Hence, the delta at the end of the plate. So, therefore, the delta, and L is 1 meters, right. So, delta comes out to be right, or okay, 13.5 millimeters. Okay. So, we will come back and sort of take a look at what do all these things mean, right. So, then again, so if let me go to the next page. So, now again the displacement thickness at the end of the at displacement thickness is given by 1.721 under root REx, right. So, well, I mean, you can straight away go ahead and find this out, all right. So, there are things you can play around with also. For example, you can find that out straight away, replace x by L and do that. Now, I did something is basically 5 by REx, right. So, therefore, delta star, right, by x, I'm going to multiply by x by delta, which is equal to 1.721 by REx into under root REx by 5. It just saves you a little bit of math. It's just, I mean, how it's just playing around with the formula, right. So, if I do that, right, so then all I get is delta star. If I use this, I think what you should do is go and cross check by using this formula and see what you get. Okay. So, now delta star is therefore equal to 1.721 by 5 into delta, right, and what I get as 4.65 millimeters. Okay. Again, theta, I think we had developed a relationship for theta as well, right. Let us go back here. Yeah. So, we had theta to be this, for this. So, let us write that down. It was what, 0.664, yeah. So, now theta again, this is the momentum thickness. Okay. So, theta by x right. So, go ahead and use this, okay. Use this formula and find out theta by replacing x by L. Okay. And you could also use something called a shape factor. Okay. Now, this is also typically used. Now, these are several parameters. which one uses to in terms of understanding, you know, the behavior of a boundary layer. So, you know, slowly we, you know, you'll get a hang of it. So, shape factor H is nothing but that, you know, the displacement thickness by the momentum thickness, and this is actually, you know, given to you for a flat plate. This value is actually known, right? It's around 2.6. So, using this you can find out, because now you know delta star and you know theta, so you can find that out. So, anyway, whether you use this formula or use this, what you get here is essentially this. So, theta is 1.79 millimeters. Okay, this is what I get. So, so similarly, all right. Now, this one was, this first case was for air, right. So, the fluid was air, and you need to do the same thing for the second case. So, go ahead and do that. That bit you can do, although I will give you the, you know, I will tabulate the values that we get, right. So, we have laminar boundary layer, right, past 1 meter by, what is the width of the width? 3 meters, right. So, past this is L, right, flat plate, okay, where free stream velocity is 2 meters per second, right. We have that. Now, in one case the fluid is air, okay, and the other case the fluid is water. Okay, fluid is water. Let me just say that. Okay, so then in at the end of the boundary layer, okay, so no, let's just say first the total drag. Okay, so the first case, the CD. Okay, now the CD, then we have the total drag, right. Then we have delta. I'm going to write L because that's at the end of the plate. Delta L, delta star L, and theta L, right. So that's at the end of the plate. So what we get for air, right? What we get for air, for CD, I'm just this is something that we did now. Okay, total drag we got as 0.0265, that's in newtons. We got this to be 13.5 millimeters. Then we got delta star to be 4.65 millimeters and theta to be 1.79 millimeters. Okay, and I will give you the values that I get for using water. You go cross check this. Okay, so okay, and also what we calculated here, the Reynolds number will change, right? So in this case, and what is the Reynolds number in this case? In this case, it was 0.137 into 10 to the power 6, right. And in this case, the Reynolds number, so Reynolds number based on the length, and here what this is 1.96 into 10 to the power 6. So 1.96 million and 0.137 million. So basically both are less than 5 million. So therefore both are laminar boundary layer. So these parameters that we've developed or we calculated or evaluated, these are all for laminar boundary layer. Okay. So then CD in this case, in case of water, is 0.00949. Okay. Drag is 5.7 newtons. Okay. Drag is 5.7 newtons. Now delta, like delta L is 3.57 millimeters. Okay. So 3.57 millimeters delta, right, and delta star is 1.23 millimeters, and this is 0.48 millimeters, right. So, this is very interesting here. Okay. So, let us see now for air, right, at you know, whatever given temperature. Let me just write down here. So, the density of course is 1.23 kg meter cube, and kinematic viscosity for air is 1.46 into 10 to the power minus 5 meter square per second. Okay? And for water, density is 1000 kg meter cube, and kinematic viscosity is 1.02 10 to the power minus 6 meter square per second. Okay. Now, what we see here is that the same plate, right, that the same plate. So, essentially, you know, when you are using, you know, a fluid which is literally whose density is 1000 times more than that of air, you know. But so what you see here is that if you have water, I guess this is not something that one is surprised, right? One would expect this. So then we get a CD which is however much less, you know. CD is very small, and here the drag is 5.7 newtons. You can see, I mean, it's even like more than 100, way more than 100 times. You can calculate the amount of, you know, how high it is, the drag, you know. It's the same plate, you know, same initial velocity, except that it is water and causes nearly 6 newtons of 6 newtons of drag, and this you can say 0.03, you know, newtons of drag. Now, the height of the boundary layer you can see is way less, obviously, right? It's a thicker, way denser fluid. Okay, so it is 13.5. It is 13.5, and this is, you know, about 4 millimeters. Okay, or 3.8 millimeters. So sorry, 3.6 millimeters actually. The displacement is around 5 millimeters, and this is about just 1 millimeters. So, so the displacement of, you know, air due to the existence of the boundary layer is, you know, 5 times more than the displacement of water to the existence of the water boundary layer, and around 1.8 millimeters is the momentum thickness, right. So, basically that is the height required to counteract the momentum deficit due to the existence of the boundary layer, and this is about 0.5 millimeters. Okay. Now, there is something else I think we had talked about. So, regarding relationship between all these things, we had also said that delta star, right, is about 1/3 of delta L. I think we had said that somewhere. So, see if that is making some sense to you, you know. It's so delta, basically delta star, okay, almost 1/3 of delta L. Okay. Fine. So, this is a, so these are the kind of things that one would like to quantify. Okay, this is how your knowledge of understanding, knowledge and understanding of the boundary layer, okay, boils down to a physical problem. That how, I mean, you know, formulae and understanding and control volume is fine, but how do you actually use it, or is it useful at all? I think that is the question. Okay, so in keeping with that, in keeping with that, let us now do another problem, okay, and kind of build on this a little more. Okay, try and sort of dwell on this for some more time. Okay, for another module at least, where let us discuss the displacement thickness, what we understand by that, and also try to answer a question which I think I had posed in the couple of initial modules. Okay, so let us revisit that and see if we are able to answer that now, if things make sense to us. Okay, so let us go and so pose this problem. Okay, now this is a kind of a problem where we're trying to design a wind tunnel. Okay, in case you haven't seen a wind tunnel, so this it's called and it's I mean from the just the layman's point of view is just a large pipe through which wind moves. That's why that pipe is basically the tunnel through which wind moves. Now we use that to do research, okay, and to study things, okay, to study the effect of things, and also these things, for example, this plate that we try to find out, all the boundary layer thickness and things like that. You could do that in actually a wind tunnel, right? You could go and set up an experiment and do that. Okay, so this is the problem here. Now, a small low speed wind tunnel is being designed, okay, is being designed. Okay. Now, the test section of the wind tunnel of the wind tunnel, okay, is 30 centimeters in diameter, and 30 centimeters in length. Okay. The flow through the test section should be as uniform as possible. Okay. Let me write that. So, the flow through the wind test section should be as uniform as possible. So, let me finish the question and then we will come back and sort of understand what a lot of these terminologies come up in problems. So, we do not even understand that, right. We just go and just find out how we can use the formula so that we can get a final answer, right. Let us not do that. Let us try to understand, or let us try to, if we do not understand, then we will have to ask more questions and figure out if we do understand it. Okay. Okay, the wind tunnel speed ranges from the wind tunnel speed ranges from 1 to 8 meters per second. Okay. Now, the design has to be optimized for an airspeed of 4 meters per second through the test section. The design has to be optimized, right, for an airspeed airspeed of 4 meters per second through the test section. So, the question is okay, for nearly uniform flow, okay, for nearly uniform flow, okay, of 4 meters per second at the test section inlet, okay, by how much okay, will the centerline airspeed airspeed accelerate, okay, by the end of the test section, by the end of the test section. Okay. That is the first question. And the second question, okay. So, recommend a design, okay, recommend a design that will lead right to a more uniform test section flow, to a more uniform test section flow. Is that right? Okay. So, now, so we can see that it's like a slightly elongated question, right. Now, what do we understand? So, let us sort of go back here, okay. Let us look at these things. Now, we are saying a small. Now, what does small mean? Well, small basically means that when you are talking about test section, right. So, the the things that you will test, they can't be like really large, it's small. So, that's what you mean by small, that the test section itself is small. Low speed, so that basically will say what? Low speed is, you're talking about something to do with Reynolds number. So, that will boil down to whether your boundary layers is, and where is the question of, and this is something, this is a question. There is no question of any boundary layer or anything at all, right. But low speed will generally decide whether your flow is laminar or turbulent. Okay. So, that will depend on the, when you say low speed, it's kind of intuitive to say that this is, the flow is going to be laminar. Okay. Okay, test section. So, what I will do is, let me first draw a schematic of this. Okay. Let us go and draw a schematic of this. So, this is my wind tunnel section. So, let us say okay, that's going to be that. Okay. Then, okay. So, now okay, then so you've got basically, so let's label what part, this is basically my wind tunnel. Okay. Now, let us do this. So, what I am going to do here is okay. So, this bit, this bit, this is your test section. This bit is nothing but your, this is your test section. Okay. This is your test section. Okay. So, when you see here, this bit is the diffuser. Okay. This is the diffuser. One will have a fan somewhere here. Okay. We'll have a fan somewhere here. Okay. Okay. So, that is the fan. Okay. These things make a lot of noise, so we will have a silencer somewhere over here. Okay. This is the silencer somewhere over here. Okay. So, now what is happening is, so we have got flow which comes in, it just comes in, there is no like uniformity, it just comes in. So, what you do is, usually this is going to be, sorry, this is like, okay. Now this is a flow straightener. So, usually you pass it through like a sieve or a mesh. Okay. So, let us just call this. So, this flow straightener. Right. So, you see flow is coming in from in various directions. Now, you want when you are so used to drawing velocity profiles like this. Now, clearly you can't expect that actually when the wind is going to come in nice and parallel streams of flow, right. So, that is what we are talking about. So, that is that, okay. And let us say this bit is say A and B. So, A is the inlet to the test section. So, or let us do that. Let us do this and just say that this here, okay, this here, okay. So, this bit, okay, now, okay, this is way too much. Okay, so okay, so this bit here, this is the inlet and this is the outlet, right. This is the inlet and this is the outlet. And so, you have, so when I have flow coming in, I would want it to be nice and smooth like that. Okay. I would really want it to be like that, and when it comes out of this also, I want it to be as uniform as possible. So, basically when it goes out of there. So, what does the fan exactly do? It is kind of helping the flow, it is trying to suck in the flow from this, from this part into the towards this here end. Okay. So, this is pretty much what the problem is all about. So, we need to find sort of what is coming in. So, 4 meters per second at the inlet. So, this is 4 meters per second at the inlet. Now, let us stop here and we look at this problem and let this engage yourself a little bit with this, try to work on this, and I will come back and solve this in the next module. Okay. So, that is a close for this module. Thank you.